Welcome everyone to a new video. Today we're going to cover section 2.6, the inverse of a matrix. So, key terms that you want to be familiar with is inverse, invertible, and singular. Okay. Really, our whole goal this section is to learn how to compute an inverse. So, before we tell you what an inverse is, let's take a look at this 3 by 3 matrix multiplied by another 3 by 3 matrix. Okay, so we know we have a 3 by 3 multiplied by a 3 by 3. The number of rows of the second matrix matches the number of columns of the first matrix, so this is a product that makes sense. The resultant is going to be a matrix that is 3 rows and 3 columns. Okay, so this is 3 by 3. Okay, let's see what we get. First off, row 1 times column 1. So we'll take this row of the first matrix, multiply it by this column of the second matrix. What do we get? 2 times a half, that's 1, times 0, times 0. So we get a 1. Okay, going down to the second row, we get 2 times a half, that's 1, minus 5 halves, plus 3 halves. Minus 5 halves plus 3 halves is minus 1 times a positive 1. Sorry, I said times plus a positive 1. Well, that ends up being 0. Okay, sliding down to row number 3, we get minus 1 half plus 0 plus 1 half. That is 0. Okay, so when you look at multiplying this matrix times the first column, you get the result 1, 0, 0. What happens if we slide over to the middle column? Okay, 2 times 0 is 0, 0 times 1 is 0, 0 times 0 is, well, that's 0. 2 times 0, 1 times 1 is 1, 3 times 0 is 0, so we got 1. Negative 1 times 0 is 0, that's 0, that's 0. We get 0, 1, and 0. Okay, moving on to column number 3. Okay, 2 times 0 is 0, negative 3 times 0 is 0, 0 times 1 is 0, this is 0. 2 times 0, negative 3 times 1, that's negative 3. 3 times 3, that's positive 3, so add those together, you get 0. Negative 1 is times 0 is 0, 0 times negative 3 is 0, 1 times 1 is 1. Okay, so when it's all said and done, you get the resultant matrix is the identity in with 3 rows and 3 columns. Okay, so here's our definition. Let A be a square matrix, okay, as this is. The inverse of A, which we'll denote as A inverse, is a matrix of the same size, okay, where A times A inverse is I, and A inverse times A is I, the identity matrix. So what you can say is, if you call this matrix A, then this matrix right here is A inverse, because A times A inverse is I. Now, it can be shown that if I were to reverse this product and start with A inverse, I can multiply it by A and get the identity right back as well. So, not all matrices have an inverse, okay? But those that do are called invertible. Okay? Those that don't are said to be singular, okay? So a lot of times words like singular and non-singular are thrown around. Okay, just remember that those matrices that are said to be non-singular are the ones that are invertible. Okay, and those that aren't invertible are singular. So why do we even care about this? Well, it's because it helps us solve systems of equations. Okay, so if you had something like a system that gave you a matrix equation ax equals b, you can multiply both sides of this matrix equation by the inverse to a, since we know it exists. Okay, again, not all a's will have an inverse, but those that do, you can multiply on the left-hand side by a inverse. Okay, and what are you left with? A inverse times a is the identity matrix times x. Now, the identity matrix is the matrix of ones and zeros, whereas ones on the diagonal, zeros on the off diagonal. You multiply that by the vector x, you'll get the vector x right back. Okay, on the left-hand side, it's a inverse times b is the product. So you can see that the solution to your system of equations that gives you the matrix equation ax equals b, is the vector x equals a inverse b. So it's a quick way to solve systems of equations. All right, let's explore that a little bit further. Okay, first off, I give you three matrices, 2 by 2s, A, B, and C. I want you to compute BA and CA and tell me which one, if any, is A inverse. Okay, so let's take a look. What's BA? BA is going to be, remember order matters here, so 3, 5, 1, 2 times 3, negative 1, negative 5, 2. So 3 times 3 is 9, plus 5 times negative 5. So that's 9 minus 25 is negative 16. Okay, well, right there, I can stop. Because I know that B cannot be the inverse to A. Because if it were, and I multiplied B and A together, I wouldn't get negative 16 there. I would get a 1. Okay, now I will keep going just for the sake of the problem so that we can get experience with matrix multiplication. So that's 3 minus 10, that is negative 7. negative 3 plus 10 is positive 7. And negative 1 plus 4 is what? 3. There you go. Next one, I'll do in a different color. What about C times A? All right, so C is 2153. A is 3, negative 1, negative 5, 2. What is this product to be? Here, 2 times 3 is 6. 1 times negative 5 is negative 5. 6 minus 5 is 1. That's promising. 5 times 3 is 15. Minus 15, that's 0. Still promising. Negative 2 plus 2, that's 0. And negative 5 plus 6. All right, there you go. We have a winner. So this matrix that we are calling C is actually A inverse. So that's A inverse. And that matrix, when multiplied by A, gives us the identity matrix. So if we were to use this information to solve the system provided, okay, which not coincidentally, okay, if I took this system in order to write it as a matrix equation, I would have the coefficients 3, negative 1, negative 5, and 2 is my coefficient matrix times x1, x2 is equal to 4 and 7. So this is of the form AX equals B. Okay, we know that the inverse to A exists. And we know what the inverse is. It's right here. It's the matrix C. So the solution to this is X equals A inverse B. So let's compute that. X equals A inverse. By virtue of the example we've just done, we know A inverse is 2153 times B. B is 47. What does that give us? 8 plus 7 is 15. 20 plus 21 is 41. So, the solution to our system of equations is x1 equals 15 and x2 equals 41. Let's see if that makes sense. If I plug 15 in for x1, 3 times 15 is 45. 45 minus 41 is 4. And, that's a computation that I really don't feel like doing right now. Negative 5 times 15, that looks like negative 75, plus 2 times 41, that's 82. So negative 75 plus 82, yep, that's 7. Perfect. So that's why we care about invertible matrices. Okay, that's one reason why we care about invertible matrices. All right, moving forward. If A is invertible, then A has a unique solution. What is that solution? X equals A inverse B. And notice that this doesn't work just for 2 by 2s. It works for 3 by 3s, 4 by 4s, 5 by 5s, but it doesn't work for anything that's not square, because to compute the inverse of a matrix, the matrix that you're computing the inverse of has to be a square matrix. Okay. By the fact from last time, we know that there's a pivot in every column of the coefficient matrix, since after all, A is going to be a square matrix. So therefore, it must be row equivalent to the identity matrix. Okay. So that's an important fact right there. Okay. And right now, I'm going to assert it as a fact. Okay. So it can we can move forward with the next step, which is how to compute A inverse. Okay, so it's going to be unsupported fact right now. In total, an n by n matrix, A is invertible if and only if it is row equivalent to the identity matrix. In other words, okay, if A is invertible, we know that A times A inverse is I. If A inverse has column vectors v1, v2, and v3, we know the product of A and v1 has to give us 1, 0, 0 down the first column of the resultant vector. Okay, A times v2 has to give us 0, 1, 0 down the second column of the resultant vector, and A times v3, 0, 0, 1. We actually saw that in the opening page when we multiplied A by v1. This is representing by v1. We got 1, 0, 0. When we multiplied the matrix A by v2, we got 0, 1, 0. When we multiplied A by v3, 0, negative 3, 1, we got 0, 0, 1. So we've already seen that property in action. Okay, here's how it helps. Okay, it's like solving 3 separate systems of equations, because really, what do we want? We want to know what vector, what v1 that you multiply A by and get 1, 0, 0 out. And then we say, well, what v2 would you multiply by A and get 0, 1, 0 out? And what would v3 be that you multiply by A and get 0, 0, 1 out? Okay, so it's like doing 3 systems of equations all at once. And the one way to do it is to perform row reductions, just like we did in last section. But the calculations, so when you do a row reduction, that's, we're trying to show that A is row equivalent to the identity matrix. So we need to put it in row echelon form, and then we put it in reduced row echelon form, et cetera, et cetera, et cetera. But when we do it, please note that the steps that we would be making in solving each one of those, each one of these would be the same. Because to get a row equivalent to the identity matrix, it doesn't matter what we're multiplying V1 by, okay? It's still going to be the same set of steps that you use to put A in reduced row echelon form. Okay, we do it for this one, we do it for this one, we do it for this one, so why not do them all at the same time? So what we're going to do is we're going to take these steps with an augmented matrix with 3 augmented columns instead of just 1. Now, at this point, you row reduce. You'll take A, you'll augment it with the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Again, this is for a 3 by 3 case. Okay. If it was a 4 by 4, this would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, etc. And we try to row reduce it so that on the left-hand side of the augmented matrix, we get the identity matrix, okay? And on the right-hand side, we get the columns V1, V2, and V3 of A inverse. Now, if what you start with, the A, doesn't reduce to the identity matrix, then the matrix is not invertible. Okay, so here we go. Compute the inverse of 1, negative 1, 2, 2, 1, 11, 4, negative 3, and 10. Okay, so let's do that. I have a scratch piece of paper here because there's no way that's all going to fit on the same. So we're going to start with A, and we'll augment with the identity matrix. So what does that give us? 1, negative 1, 2, 2, 1, 11, oops, 4, negative 3, and 10. And we'll augment with 1, 0, 0, 0, 1, 0, 0, 0, 1. All right. So through elementary row operations, I'm going to make everything in green the identity matrix. Okay. So first step, I'm going to take and replace row 2. So the new row 2 is going to be equal to 2 times the old row 2 minus row 3. So the old row 2 is going to be multiplied by 2. So I'm going to get this to be, I'll do my work. It's all going to be right here. So I'll do my work right here. That's 4, 2, 22. Oh, geez, that doesn't look good. 4, 2, 22, 0, 2, 0. Okay, because I'm multiplying this by 2, multiplying this by 2, multiplying this by 2. And I get 4, negative 3, 10, 0, 0, 1. And I subtract. 4 minus 4 is 0. 2 minus a negative 3, that's going to be 5. 22 minus 10, that's 12. 0, 2, and negative 1. So our new row 2 is going to be 0, 5, 12, 0, 2, negative 1. And that's 0, 0, 1, and that's 1, 0, 0, and that's dot, 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 and that's 1, negative 1, 2, and that's 4, negative 3, 10. Okay, so we're trying to put this in row echelon form. So we have a pivot right here in the first column. There's a 1, so there needs to be zeros below it. So that means I need to get rid of this 4 down here. So I'm going to say my new row 3 is going to be equal to 4 times row 1 minus row 3. So what's 4 times row 1? 4, negative 4, 8, 4, 0, 0. And we subtract. 4 minus 4 is 0. That's a negative 1 right there. Negative 4 minus a negative 3, so that's plus. 8 minus 10 is negative 2. 4 minus 4. Right. So what do we get? We get this to be 0, negative 1, negative 2. And this is 4, 0, negative 1. Dot, dot, dot. 0, 2, negative 1, 1, 0, 0. All right. So first column looks good. Now let's deal with the second column. So we go over a row and down a row and repeat the process. So I need this to be a 1. So really what I should do is I should swap row 2 and row 3 and divide by negative 1. Okay, so I'm going to say the new row 2 is going to be the old row 3 times negative 1, and the new row 3 is going to be the old row 2. That's easy enough. So it's 1, negative 1, 2. This is 0, 1, positive 2, because I'm multiplying the old row 3 by negative 1. So that makes this negative 4, 0, positive 1. This is 1, 0, 0. This is going to be 0, 2, negative 1, dot, dot, dot. And this is 0, 5, and 12. Okay. So now I need to make this a 0. So my new row 3 is going to be 5 times row 2 minus my old row 3. So let's see what we get. 5 times row 2, that's 0, 5, 10, negative 20, 0, 5, 0, 5, 12, 0, 2, negative 1, and subtract, so that's 0, 0. 10 minus 12 is negative 2. That's negative 20, that's negative 2. 5 minus a negative 1, that looks like it's 6. So 1, negative 1, 2, 0, 1, 2, 0, 0, negative 2, dot, 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 negative 20, negative 2, and positive 6. It's negative 4, 0, 1, and 1, 0, 0. All right, so now I need this to be a 1. We have a 1 followed by a 0. Let's make this a 1. So row 3 is going to be row 3 times negative 1/2. So it's 1, negative 1, 2, 0, 1, 2, 0, 0, 1, dot, dot, dot. So if I'm multiplying by negative 1/2, that makes that a 10, that makes that a 1, that makes that a negative 3. Nothing else changes. All right, so now this is row echelon form. Okay, my pivots are on the diagonal. Everything below a pivot is a 0. To put it in reduced row echelon form, everything above a pivot has to be a 0. So now that means I need this 2 to go away. I need it to be a 0. So I'll say my new row 2 is going to be what? Let's call it my old row 2 minus 2 times row 3. So my old row 2 is 0, 1, 2, negative 4, 0, 1. My old row 3 is 0, 0. I'm going to multiply it by 2, so that's 20, that's 2, and that's negative 6. And then what do? I subtract. So that's 0, 1 minus 0 is 1. 2 minus 2 is 0. That's negative 24. That's negative 2. 1 minus a negative 6, that's 7. So it looks like this is 0, 0, 1. 0, 1, 0. That's 1, negative 1, 2, dot, dot, dot. This doesn't change. 10, 1, negative 3. 0, 1, 0. That's negative 24, negative 2, and 7. And this is 1, 0, 0. All right, folks, we're getting there. Sorry, this is not the most fun, entertaining television that you've seen. I need this to be a 0 now, the 2 that's up there. So my new row 1 is going to be my old row 1 minus 2 times row 3. So my old row 1 is 1, negative 1, 2, 1, 0, 0, 0, 0, 1. Oh, sorry, that's multiplied by 2, so that's 2. That's 20, that's 2, and that's negative 6. Okay, and we subtract. So that's 1, that's negative 1, that's 0. 1 minus 20 is negative 19. 0 minus 2 is negative 2. 0 minus the negative 6 is positive 6. So we get 1, negative 1, 0. This is 0, 1, 0. This is 0, 0, 1. We get negative 19, negative 2, and 6. Then that's negative 24, negative 2, and 7. That's 10, 1, and negative 3. Beautiful. Almost there. The only thing we need now, we have, there's our pivots. Everything below our pivot is a 0. Everything above this pivot, well, there's nothing above this pivot. Everything above this pivot are zeros, but not above this pivot. So I need to make this negative 1 a 0 by one more step. Our new row 1 is going to be our old row 1 plus row 2. So 1, negative 1, 0, negative 19, negative 2, and 6. And I'm adding to it row 2. So when I add, what do I get? 1, 0, 0. Negative 19 plus negative 24, that looks like it's negative 43. That makes sense. That's negative 4, and that's 13. So we get this to be 1, 0, 0, negative 43. Oops, sorry, this slide is in red. So that's negative 43, negative 4, and 13. This is negative 24, negative 2, and 7. This is 10, 1, and negative 3. What do we get on the left-hand side? The identity matrix. So this right here is the identity. And this right here is A inverse. Hallelujah. So, everything in red, negative 43, negative 413, yada, 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 is the inverse to what we started with, the matrix A. All right. Now, should you check me? Yes. Is it possible that I made a mistake? Absolutely. Okay. There's no way that I'm going to be perfect. Well, I shouldn't say that. It's very possible that somewhere in this mistake, I've got a negative mistake. I added 2 and 2 and got 5, something along those lines. Okay, but this is the process that you would do to compute A inverse. All right. So, next thing is use the information that we've just found. So let's write that down here. So, according to my previous work, I had a calculator around here somewhere, but it seems to have vanished to confirm my answer. A inverse is negative 43, negative 413, negative 24, negative 2 and 7, 10, 1, and negative 3. So now that I know what A inverse is, use A inverse to solve this system of equations. Okay, so remember, A is the coefficient matrix: 1, negative 1, 2, 2, 1, 11, 4, negative 3, and 10. Okay, so this right here is another way of saying A times X equals B. Because A is invertible, okay, we know the solution to this system is X equals A inverse B. So all I'm going to do to solve this system is to multiply A inverse by B, negative 1, 3, and 2. All right, so this is A inverse B, A inverse B. What does that give me? Hopefully something nice. Negative 43, so that's positive 43. Minus 12 plus 26. So what is that? 26 and negative 12, that's 14. 14 and 43 is 57. A negative 24, that's positive 24, minus 6, plus 14. So that's 8 plus 24, that's 32. And negative 10 plus 3 minus 6. So that's minus 16 plus 3, that's negative 13. Yeah. So, according to the work that I just did, x1, the solution is x1 equals 57, x2 is equal to 32, and x3 is equal to negative 13. I'm kind of nervous, but let's give this a try. We'll plug this into equation 1 and see if I get a true statement. If not, then I've made a arithmetic error somewhere. So if x1 is 57 minus x2, that's 32, plus 2 times x3, x3 is negative 13, so that's 2 times that's negative 26. So negative 26 minus 32 is negative 58. Negative 58. 57 minus 58. That's -1. That works. Perfect. So, I'll leave it to everyone else to check and see if x1, x2, and x3 make the second row true and make the third row true. But the fact that it makes the first row true makes me feel a little bit better than I did about 2 minutes ago. All right, so finishing off this set of notes, I'm just going to state a theorem. The inverse of the inverse, so A inverse inverse is A. It's kind of like how A transpose transpose was A. Number 2, second part, if I take A and B, multiply them together, and then compute the inverse of that, that's the same as saying B inverse A inverse. Okay, there was a transpose analog to that. AB transpose was B transpose A transpose. Okay, and lastly, A transpose inverse is the same as A inverse transpose. Okay, so those are all theorems that you can use for free without proof. They're not too difficult to prove. But this video is long enough, and you've been patient getting through the very end of it. So I hope this takes you towards solving all the questions that you'll come across in homework for section 2.6. If not, again, please feel free to stop by office hours. And again, as you're doing this work, okay, I understand it's very easy to make a bonehead mistake. Okay, make sure you're showing your work here. That's how you get partial credit. Okay, so if you add 2 and 2 together and get 5, I can look back and say, oh, well, this is where the mistake happened. So, grade as though that were correct. Okay, where if you don't include this right here, I may not understand how you replace row 1 and what you replaced it with and yada, yada, yada. Okay, take care. Have a great one.